10.4, perimeters and areas of similar figures. Now we know similar figures, corresponding angles are congruent and corresponding sides are proportional. So today we're going to talk about the perimeters of areas and similar figures. Our theorem says that if your scale factor, remember that is the ratio of the sides, the lengths of the sides, the scale factor of similar figures is A to B. So let's draw a couple of similar figures here. We have two squares. One of them has side lengths of 3, and one of them has side lengths of 5. This tells us that the ratio of the perimeters is also A to B. So let's find our scale factor. We know that the scale of our two squares, small to large, is 3 to 5. So if this is A to B, let's look at our perimeters. Perimeter is the sum of all of the sides, the distance around the outside. So this one is going to be 12. Perimeter of figure 1, perimeter of figure 2 is going to be 20. That is going to give us a perimeter ratio of 12 to 20. Now if we reduce this, divide by 4 top and bottom, that gives us a ratio of 3 to 5. Notice this is also A to B. Let's mark figure 1 and figure 2. Now let's look at the areas. It says the ratio of the areas is A squared to B squared. Now this should make sense because area is squared. Let's look at the area of figure 1 here. The area of figure 1 is 9 units squared, and the area of figure 2 is 25 units squared. So our area ratio is 9 to 25. Now be careful, this does not reduce. But if we look at this, this is A squared to B squared. Our A was 3 squared. Our B was 5 to 5 squared. Let's do an example. It says the trapezoids at the right are similar. The ratio of their corresponding sides, if we look, we're going to find our scale, is 6 to 9, which reduces down to 2 to 3. It asks us to find the ratio of the smaller to larger, be careful there, of the perimeters. We know that perimeter ratio is the same as our scale factor, so that's just going to be a ratio of 2 to 3. Now the next part asks us to find the ratio, smaller to larger, of the areas. We know that the area ratio is our scale factor squared. So 2 squared to 3 squared. Our area ratio is 4 to 9. Pause the video and try the next example. Now you should have seen that you were given the ratio of 5 to 7 for two similar polygons. But as we looked into the problem, we saw that they wanted the ratio of larger to smaller. So we wrote our scale factor as 7 to 5. Our perimeter ratio is the same, 7 to 5. And our area ratio is our scale factor squared, so 49 to 25. This allows us to find missing parts. If you know the area of one of a similar polygon, you can find the other area using a proportion. We're going to be using proportions again. So in our example here, we are told that the smaller pentagon has an area of about 27.5 centimeters squared. We are looking for the area of the large pentagon. So first, number 1, we find scale factor. Number 2, we find perimeter or area ratio. And then number 3, we're going to use those to write a proportion. So for these two figures, we look at our lengths and we find that scale is 4 to 10 or 2 to 5. From that, we know that our area ratio is 2 squared over 5 squared, which is 4 to 25. That lets us write a proportion, and we know that our small figure is on top, our large figure is on the bottom. We solve this, and x is 171.9, and our unit, centimeters squared, for the area of the large figure. Pause your video and try the next example. Okay, we were told that our scale factor was 3 to 4 and that the area of the larger parallelogram is 96 inches squared. So we find our area ratio is scale squared, so 9 to 16. We use that to write a proportion. Remember to keep your small and large in the same place. We solve that, and the area of the small comes out to be 54 inches squared. When you're doing these problems, you need to think about, are we talking about a perimeter, a length? Are we talking about the sides, or are we talking about an area? That helps you determine which ratio to use. In this example, our students are growing vegetables on a plot of land. Next summer, they want to use a similar plot where each dimension is 2.5 times the original plot. This tells us we're talking about area. So we find our scale. Our scale is 2.5 to 1. And here we are talking about new to old. And so that lets us write an area ratio. We square that, 2.5 squared over 1 squared. And then that lets us write a proportion. So 6.25 to 1. And in the old, we got 13 bushels. X is going to give us the new bushels. We solve that, about 81 bushels. Pause the video and do the next example. In example 3a, we were given a scale factor of 3 to 5 and told a smaller piece of glass costs $2.50. If you think about a piece of glass, you are talking about an area. So we use our area ratio. We can write a proportion. Make sure to keep the small and the large in the same position in your proportion, and we solve and find out the large piece of glass is going to cost $6.94. In example 3b, it asks us why it's important that each dimension increases the same amount, because we know that in similar figures that your sides are proportional, so your sides must increase proportionally. They must increase by the same amount. Okay, let's do the next part here. Now, you can use these ratios to work backwards. We are given two triangles here, and we are given the areas. So we know that we have an area ratio. Area of the small to the large is 50 over 98. Now, what do we know about our perimeter ratio? We know that area ratio is squared, So our perimeter ratio is going to be the square root of our area ratio. Now, if you look over here in the example, they have reduced their numbers. Smaller numbers are always better. And what did they find? They found perfect squares. We can simplify our radicals. So if I want to simplify 50, the square root of 50, I get the square root of 25 times the square root of 2. This is 5 root 2. If I want to simplify the square root of 98, that factors into the square root of 49 and the square root of 2. You really had to check some perfect squares to find that one. And I get 7 root 2. So my perimeter ratio is now 5 root 2 over 7 root 2. And look, top to bottom, that is going to cancel. Square root 2 on the top cancels with square root 2 on the bottom. And we get a perimeter ratio of 5 to 7, which is the same thing we got over here. So you can simplify these by reducing down first, always a good idea, or by simplifying your radicals. So let's look at our last example here. Why don't you pause the video and try this one. All right, this one was a little tricky. We were given the areas of 2 similar rectangles, and I chose to put mine small over large. You could have put yours large over small. It doesn't matter. It only matters if you are directed to which one needs to go first. And we need to find the ratio of the perimeters. So I wrote my area ratio here and here. And then I decided I don't like those big numbers, so I want to reduce them down. I noticed they were both divisible by 5. And then I noticed that they were both divisible by 3. This gets us down to much better numbers. I see a perfect square there already. So I can write my perimeter ratio, which is going to be the square root of the area ratio. The 9 is going to work out nicely. It's a perfect square, but I have to simplify my 125 radical. That simplifies down to 5 square root 5, so my perimeter ratio is 3 to 5 square root 5. Now, we don't always like to have a radical in the denominator. For a ratio, it's not as bad. But we can rationalize that, and we get 3 square root 5 over 25. And we can write our ratio this way.